Our last key NMR analysis technique is based on chemical splitting. Now, as we've talked about NMR, right, so we have our individual hydrogen nuclei with their nuclear spin generating that magnetic field. And we've seen how that spin can be affected by things like electrons, right? So we have a magnetic field from our electron, which can work against our external magnetic field, and it can affect the overall magnetic field that our individual nuclei experiences, right? So that was our old equation, right, where our effective magnetic field is equal to that external magnetic field minus the magnetic field of our electrons. Now again, one of the key things that I've said is that when we have a charge that's rotating, it creates a magnetic field, right? So if we have one hydrogen, it generates a magnetic field. But if we look at other hydrogens nearby, right, so we have these hydrogens over here. So all of these essentially look the same in group 1. But now we have these hydrogens over here in group 2 that also have a magnetic field. And this magnetic field can actually influence the magnetic field of my hydrogens over here, right? So our hydrogens can actually be affected by other hydrogen nuclei and their magnetic field, and not just the magnetic fields from electrons. So we actually have to add a new component on here that relates to essentially the magnetic field of our other hydrogen atoms, right? So this is going to be an additional term. This can either add to our effective magnetic field or oppose it, depending on what the spin state of our other atoms looks like. So if we look at this group of hydrogens together over here, so this is going to be group 1. They're going to be affected by the state of each of our hydrogen atoms over here in group 2. Now, let's go to a simpler case here first. So let's go to this molecule here. So we have these hydrogens all look the same, right? So they're all equivalent. So this is group 1 is all of these hydrogens, and we have group 2 as this hydrogen here. So all of these get affected by the spin state of this one hydrogen, right? So we know that this can either be spin plus 1/2, spin up we'll say, or spin minus 1/2, spin down. If that spin is up, it's going to affect our magnetic field in a positive direction, versus if it's spinning in the opposite direction from us, it's going to have a negative effect on our magnetic field, right? So it can actually affect our peak depending on whether it's up or down. So if we have, so here's our peak based on what frequency we absorb based on our chemical environment. And now half the time, let's say this is going to be pointing up, and the other half the time it's going to be pointing down, right? It can be up or down. We don't necessarily know what it's going to be. So depending whether it's up or down, our peak is going to shift slightly to the left or to the right. Now, if we assume that half the time it's up and half the time it's down, that means we're going to be shifted in both directions, and we're going to end up with 2 peaks. So one that's shifted by it going up and one that's shifted by it going down are 2 different possibilities. Those are each equally probable, so we get 2 peaks that are each equal, right? We have a 1-to-1 ratio between these 2 peaks, as our peak basically shifts based on the spin state of that hydrogen atom, right? So if the spin is supporting our magnetic field, then we're going to have a larger energy gap or a higher frequency, right? So that would be to the left. So this will be kind of our spin up. And if the other hydrogen is against it, then would be slightly more to the right to our lower frequency values. Okay, so that's the simplest case, right? If we have one hydrogen atom, if it's up or down, we get 50% in one state, 50% in the other state. So let's go back to our previous alcohol molecule. So far we've learned, so let's make a column, right? So our spin state is going to, or our peak is going to be affected by how many neighbors we have, right? So if we had one neighboring hydrogen, that would result in two different states, up and down, or up or down rather. And so we end up with two different peaks. Each of these are equally probable, and so we get two peaks with 50-50 ratio. Now, let's say we have two neighbors, right? So we go up to two neighbors here. So all of our hydrogens here, group 1, they have two neighbors right here. Now, each of these can either be up or down, right? So now we have multiple possibilities. So this one could be up and that one could be down. This one could be up and that one could be up. Or they could be both down, or they could be the other one down and up. Right? 4 different possibilities. So if they're both supporting the magnetic field, that's going to give us our most, our highest frequency, our largest energy gap, right? So it would be the highest ppm. So that would give us our peak furthest to the left. Now, both of these possibilities are basically the same, right? We have one supporting, one opposing, one supporting, one opposing. So overall, these have no effect, right? So let's put these together in the middle. So these wouldn't affect our peak at all. There's two possibilities there. And then we have our final possibility of them both opposing our magnetic field. So now, if you look at this, we have one possibility here, two possibilities here, and one possibility here. And that's going to relate again to the size of our peaks in our overall spectrum, right? So we're going to have roughly a quarter of the time, we'll have both of those hydrogens pointing up, so that'll be our peak more to the left. Half the time, we're going to have them opposing each other, up and down, or up or down and up. And so we'll get our peak in the middle. That'll be twice as big as the other peak. And then we'll get a third peak from them both opposing the magnetic field. So we get a characteristic 1 to 2 to 1 pattern as we're split by interacting with the magnetic field of our two neighbors. So our previous example, we just had two different possibilities from that neighbor being up or down. Here we have three different possibilities, both neighbors being up. We have our possibility here, which is more likely, of one being down, one being up, or one being up and one being down. And then our fourth possibility of both being down. We refer to this as a triplet. This would be a doublet. You can see the number of peaks is based on the number of neighbors you have. And we can actually have this n+1 rule. The number of neighbors we have plus 1 is going to be the number of peaks that we'll see. Right? So if we have one neighbor, we have two different possibilities. We end up splitting into two different peaks. If we have two neighbors, we end up with these three different possibilities overall. So we could continue this, of course, for other numbers of neighbors as well. Right? If we have three neighbors, then we would be So one possibility would be all up. One possibility would be all down. We would have 2 up and 1 down. There's multiple different possibilities for that. Or we could have 2 down and 1 up. And there's multiple different possibilities for that. So we end up with this 1 to 3 to 3 to 1 ratio, and we would refer to this as a quartet. Okay, and then of course this could continue if you have more neighbors. You would just be adding more possibilities and then more different peaks that you're splitting into, following the standard n+1 rule. Where this gets complicated is if we have a group of hydrogens with 2 different sets of neighbors, right? So these hydrogens here are affected by these neighbors over here, right? So there's three identical neighbors. They would split us into a quartet. But then over here there's another set of 2 identical neighbors. These would split us into a triplet. So which pattern do we actually see? And the answer is we actually combine both. So we actually would get a triplet of quartets where we'd see both splitting patterns at the same time. So overall, if we were to draw this out, so we would see this triplet from group 1 as it's split by those 2 neighbors. Group 2, we'd get a very complex splitting pattern. I'm just going to show so we'd have lots of little peaks. It wouldn't look exactly like this. It would be more complicated. But I don't want to draw out the full splitting pattern. And then when we get over here to 3, we would see another triplet. So again, 1, 2, and 3. And again, still our integration pattern is the same. So the overall area of this peak would be 2. The overall area of this peak would be 2. And the overall area of this peak would be 3 relative to each other. We can combine the areas of these different split peaks because they're all based on that same group of hydrogens. So we'd combine all these together in our integration. We would combine all of these, and we'd combine all of these as well. So now from our splitting pattern, we can start to look at what our overall structure of our molecule is. Right? So again, when we have these peaks over here at lower chemical shift values, we know that means that we're far away from electronegative atoms. But that doesn't necessarily help us place that group in our molecule. Well, now if we look at our peak splitting, so 3 peaks means we have 2 neighboring hydrogens. Right? So now we know that these hydrogens are adjacent to a carbon with 2 hydrogens, as we see on our overall structure. We see the same thing over here with group 3. Since it has a higher chemical shift, we know it's closer to an electronegative atom. Since it's split into 3 peaks, a triplet, we know that it has 2 neighbors. So this is also next to 2. Our complex splitting pattern here is a little bit more difficult to analyze. But what it does tell us is that we know that this group of hydrogens here has a lot of different neighbors. So using these different tools, our chemical shift, our integration, as well as our chemical splitting, we can start to analyze our NMR spectra and piece together the overall structures of our molecules just from the information that we learn from this wonderful tool of NMR.